Today I'm going to explain you differential evolution through a numerical example. As you understand that the differential that the nature inspired optimization algorithms work in four parts: problem definition, the algorithm parameters, and then the population initialization, and the actual algorithm position update strategy. So here for differential evolution also I will use these four parts for explanation purpose. This algorithm is implemented on the problem sphere function, which is easy to explain for the working example, and with only two decision variables. In actual real world problems, the number of decision variables may be high and the problem may be quite difficult. But here for just explanation purpose, I took two variables and a very simple example sphere function. Also, I used the DE's basic version of DE. Actually, DE has many strategies based on the number of differentials, based on the selection of type of vectors for the differentials, and the selection of the crossover operator. So accordingly, DE has many strategies. I have considered the basic version of DE, which is denoted as DE1 rand win. I'll explain this meaning of this notation later during this example. So now let us start with the problem definition. As I told you that I'm going to take the problem sphere function. So in the sphere function, we need to minimize this function x1 square plus x2 square. I have considered only two variable problem. This problem is scalable and number of variables can be increased at our will. This is the search space, which is -5 to 5, means both the variables lies in the range -5 to 5. Second part is the algorithm and the problem parameters. So differential evolution and the problem parameters. First of all, first parameter for the all population based optimization algorithm is the population size. So here for this working example, I'm considering only the 5 population size. In actual implementation of the algorithm to the real world problems, this problem size is relatively very large number. Number of decision variables, which is known as the dimension of the problem, is 2, because two variables are here, so the dimension of the problem is 2. Stopping criteria is another parameter, is another decision to be taken here for the algorithm. So here this example is solved in 2 iterations, so I am considering the stopping criteria as 2 iterations. And then the scaling factor and the crossover probability, these are the two parameters of the algorithm differential evolution. I took the value of scaling factor f 0.5 and the crossover probability PCR equal to 0.7. The explanation, what the role of this scaling factor, what is the role of this crossover probability, why these values are good, I'll explain during the example. But here I just to tell you that the parameter values. The another step is the population initialization. So here, since population size is 5, so we need to generate 5 solutions randomly in the range this -5 to 5 in the search space. So in the range -5 to 5, I'm generating 5 solutions. Since it is a 2 variable problem, so it's a 2-dimensional vectors, 5 2-dimensional vectors are generated randomly in the range -5 to 5. And let me call these solutions, initial solutions, as x1, x2, x3, x4, x5. So these 5 solutions are representing the initial population, and this is the corresponding function values. Function values are calculated by just substituting these solutions, this solution to this objective function x1 square plus x2 square. So here this 1.7667 square plus -4.1337 square gives you this value, and similarly other values are obtained. Here you can easily observe that out of these 5 solutions, since this problem is of minimization type, and this for this fifth solution the objective function value is minimum, and therefore you can see that this fifth solution is the best solution in this initial iteration. In this initial population, this x5 is the best solution. Now the main differential evolution loop position update strategy. So let me first explain you the notation, the meaning of this notation DE rand 1 bin. So here this the first part, this DE stands for the differential evolution. This rand makes the random selection of the target vector. Actually DE has two parameters, crossover, mutation and the crossover. So for these two operators, we need to select some target vector, one target vector out of the current population. So for that target vector, how the target vector is selected. So this is the strategy that it is selected randomly. So this rand makes the random selection of the target vector. This one is for the number of differentials to be used in the mutation operator of differential evolution. This win is for the binary crossover in the crossover operator of the differential evolution. So overall, D stands for differential evolution. This is for the selection of the target vector. This is for the number of differentials, and this is for the type of the crossover. Let's just start the first generation or the first iteration of the differential evolution. So in the D position update, two operators we use, mutation and crossover, and it is different from other evolutionary algorithms because in evolutionary algorithms like genetic algorithm, crossover is applied first and then the mutation is applied, but D is different. Here the first the mutation is applied and then crossover is to be applied. It is so let us start the first operator of differential evolution, the mutation. So in differential evolution, the mutation operator is used to create a trial vector. Let me call this trial vector, denote this trial vector by U. So remember, the mutation operator is to create the trial vector, and this trial vector is created by mutating a target vector, and this target vector is selected from the current population of current population. And for this selection, as I mentioned here in this notation, that this target vector is to be selected randomly for our strategy, but there are many strategies in differential evolution for the selection of this target vector, right? So for the mutation, here is the update equation. This is the update equation in the mutation, or the equation of the mutation operator in the differential evolution. Remember, in mutation, a trial vector is generated. Trial vector is generated by mutating a target vector. So here the trial vector equal to the target vector plus, this is a parameter, as I mentioned, that scale factor f, which I took 0.5 in the parameter settings. So here this scale factor multiplied by this is the one differential. This is multiplied by a differential, and how this differential is created by the difference of two vectors, and now these two vectors are selected randomly. So this is your first randomly selected vector, and this is your another randomly selected vector. So randomly selected solution 1, randomly selected solution 2. So the trial vector in the mutation operator, trial vector is obtained by mutating the target vector with the help of a scale factor and two randomly selected solutions from the current population. Here it must be noted that the target vector, randomly selected solution 1, randomly selected solution 2, all three are different, and all these three are also different from the this target vector should be different from the randomly selected solution ones, and all these three should be different. Okay, the scale factor, this scale factor, theoretically this scale factor can be anything between 0 to infinity, means can be any positive real number, but the experimental studies suggest that the scale value of the scale factor should be 0.5, should be exactly 0.5 or around 0.5. It may be something 0.7, 0.6, or 0.4 also, according to the problem. You understand that for the nature inspired optimization algorithm or meta heuristic or population based optimization algorithms, the fixed value of parameter suggestion for the fixed value of the parameter is not possible. So it is a recommended value, but slight modification in this value can also work. Now to begin with mutation for the first solution, let me select the first solution for the mutation. So let me select the first solution for the mutation. Let me create a trial vector for this by mutating this. So first of all, begin with the first solution. Select the first solution as the parent vector. Now this parent vector, I have selected the first solution as the parent vector. So x1 is the parent vector. Now I need to take care that the target vector, randomly selected solution 1, randomly selected solution 2, all three must be different from this parent vector. These three should be different from the parent vector. So here you can understand from this you can understand that if you are using a one differential, number of differentials are one in the mutation operator, then your parent, then the population size in differentials evolution should be minimum 4, because for one parent vector you need three different vectors for mutation operator. So the minimum population size, if you are using only one differential, then it should be 4. Of course we have taken the 5, so there is no problem in implementing one differential in our example. So here x1 is the parent vector and corresponding function value is this. For mutation, let the target vector, and this target vector is selected randomly, as I told you that we are using this strategy where the target vector is selected randomly. So it is your x4, randomly selected solution, randomly selected solution 2. So randomly selected solution 1 is x5, randomly selected solution 2 is x3, target vector is x4. So you can see here that all four, x1, x4, x5, x3, all these four are different. If they are same, randomly generate during the random generation, if it comes equal to some other or same other as other parent vector or the target vector, then we will generate it again randomly. So we will keep on generating randomly until we have all four different. And the scale factor, I already told you that it is 0.5 we have taken. Now this is the calculation for the fourth trial vector u1. I'm denoting it by u1 because it is calculated for the parent vector x1, so I'm calling it u1. And this mutation operator is implemented component wise. Component wise means for the first component, for first parents, first component I will implement it separately. For the second component it will be implemented separately. So this mutation operator is implemented component wise. So for the first component I'm going to update it. So you can see that the first component parent vector is this, and since in the mutation trial vector is obtained by mutating the target vector, so target vectors is your 4x4 whose first component is this. So I'll write first component here x41. Your formula of course for first component will become u11 equal to x41 plus 0.5 is the scaling factor f. X51 is the first randomly selected solution, which is your x5, so it is x51. Fifth solution's first component, third solution's first component will be here, and by replacing these values from the population we'll have this, and solving this you will get this value. So your u11 is this. Similarly you will apply the same process and you will get this for the second component, and you will get this value. So we'll do it for all the components of each solution, right? So for the first parent vector you have created trial vector u1. So trial vectors is this. Now actually you need to see whether this trial vector is within the range or not, is within the search space or not. So you can see that both the components are already within the range -5 to +5, and therefore we will accept it. If this value goes, if any of these component value goes beyond the search space, suppose this value becomes 6, suppose this value becomes 6, then we will keep it to 5, and if suppose this value becomes -6, then we will keep it to -5. In other words, I want to say that the components, the updated vectors component which are going beyond the boundary will be pulled back to the boundary. So if it is -6, then it will be -5. And this is one of the many strategies for keeping the vectors, updated vectors, into the search space. Researchers have proposed many other strategies also. Some says that if it goes beyond, then you randomly generate this, but most popular is to pull it at the boundary. For time being, this trial vector u1 is within the range, both the components are within the range, so we will accept it. There is no change. And this completes the mutation process for the first parent vector. Now for this parent vector, we'll go ahead with the crossover operator. Another operator is the crossover. This is the strong point of the differential evolution, that the differential evolution has minimal number of operators and minimum number of parameters. Only two operators, mutation and then crossover, only two major parameters, the scaling factor and the probability of crossover. Scaling factor is used in mutation, probability of crossover is used in crossover operator. So in the DE crossover, an offspring is generated. You understand that in the mutation operator, one trial vector was generated. The crossover operator is implemented to generate an offspring, and this offspring is generated using the discrete recombination. How this discrete recombination is done, I'll explain. Of parent vector, in this case this parent vector is your x1, and the trial vector which is obtained after implementing the mutation, so it is u1. So here in this crossover operator, one offspring will be generated by the discrete recombination of the parent vector x1 and the trial vector u1. So you are going to do the crossover of u1 and x1. For this, I already mentioned this probability of crossover, this 0.7. Since we are going to calculate the offspring corresponding to the parent x1, so let us denote the offspring by x1 dash, right? Trial vector was denoted by u1, and here the offspring I am denoting by x1 dash. Now this offspring x1 dash is obtained using this formula, and this formula says that the jth component of the first offspring, is taken from the trial vector or from the parent vector. This depends upon this index set I. Now this creation of this index set I depends upon the type of crossover which we consider. So here we are going to consider the binomial crossover. So with the help of the binomial crossover, first of all we will create this index set I. So how it is created, I'll explain this. So in binomial crossover, crossover points are selected from the set 1, 2 up to the problem dimension. So here the problem dimension is 2, so this set is only 1, 2, and this selection is always based on the probability of crossover. Now actually this probabilistic selection from the set of these dimensions, the dimension numbers may lead to the situation when no point is selected based on this probability. So suppose this is your 0.7 and the probability, both the time the probability fails and you have not selected any point from this set. In that case, this I will be empty set. Once if the I is empty, then there will be no component in the offspring from the trial vector, and all the components in the offspring will be from the parent vector. It means the parent and the offspring will be same, and parent is the original population. You can understand that this is the original population, and after the crossover, offspring is also same as the parent. It means there is no change, and in that case D's contribution will be nil. D's contribution will be nil, and therefore we we want that this I should be non-empty set, and therefore initially randomly we will consider at least one component from this set in the I without any probability. So in the deterministic way we will select any one random index from this set for the I, and for this time let us select it is 2 out of 1 2. You have only two dimensions, so it is 1 2, and initially let I starts with 2. I hope you understand that why I take this initially as a non-empty set, and this initial entry is selected randomly from this set, which is 2 for this example. Now other points are included in this set or not included will be based on this probability of crossover, which is calculated using this formula. You can see here in this formula, for every j we will try if this is true, if the probability is true, and this j is different from already existing j, means if this is true and this j is not equal to j naught, this j naught is the index which is already inside the I. So if this j is not equal to j naught, then we will include this corresponding j to this new set I, and this I becomes I union old I union the new j. In this way we will create the set I, index set I, and then we will calculate the offspring using this formula. So the crossover operator can be understood using this selection of the creation of the I using the probability of crossover, and the creation of the offspring using this formula. So for this example, let us consider for this rand 01. In this case, this rand 01 is your 0.67. If it is 0.67, then you can understand that it is less than 0.7, and for j equal to 1, it is also not equal to j0. j0 is your 2. j0 is 2, which is not equal to, so 1 is not equal to 2. Also this probability is true, and it means this j equal to 1 will be included in this set I. So now the I will become 1 2, I equal to 1 2. Now since it is only two dimensional problem, so this process, this loop finished here, and you have a new I. Now I equal to 1 2 will tell you using this formula that since both the indices j equal to 1 and 2 are in this set I, and therefore in offspring both the components will be from the trial vector, so actually the offspring will be same. In this example the offspring will be same as the trial vector. So here this is your parent, this was your parent vector, this was your trial vector, and based on that formula you will see that the offspring will be same as the this is same as the trial vector, because both the indices are in the set I. So it is both are same, means no component are taken from the parent vector, both components are carried from the trial vector. So this completes the process. After the crossover you have generated this offspring, but as you understand that in all the population based optimization algorithm, the population remains constant, population size remains constant. Now you have one parent and this offspring, so here you need to apply the greedy selection, whether this value should be this offspring should survive in the population or this parent should survive in this population. So this greedy selection will be based on, strictly will be based on the function value. So we'll calculate the function value at this, which was 20.2089, and when you will also calculate the function value at this offspring, and you can see that the function value at this offspring is your 19.9417, which is better than this, because your problem is of minimization, so it is better than this parent vector, and therefore the offspring will survive in the population, offspring will survive, and the parent will die out. So in place of this x1, the x1 will be replaced by this offspring x1 dash, and therefore the new position of x1 becomes the position of offspring. So this is your new x1. Now this the same procedure we will apply for the another solution, next solution x2, which is now a parent vector. So let us now consider x2 as the parent vector, and this is your function value. Here again you will select target vector and two randomly selected vectors. So let me call that x5, x3 and x1, and use the same procedure, same mutation operator, same formula, and you will obtain this u2. This is the trial vector, and then again you will apply the crossover based on the same kind of application. You will create this index set I using the binomial crossover, and then you will see that again both the indices are here, both the components are here in this I, and therefore your offspring will be same as the trial vector. So this is your offspring and the corresponding function value is this. Again you will apply the greedy selection. You can see here that the function value at x2 is 23.5503, while the function value at the offspring is 1.618, which is better, and therefore this x2 dash, the offspring, will replace the parent vector x2, and therefore the new position of x2 is this, which is the position of the offspring. The same process will be applied for the third solution x3. This time the parent vector is x3. This is the target vector, two randomly selected vectors, trial vector, and now you can see here in this trial vector, after mutation you will obtain this trial vector. So in this trial vector you can see that both the components are beyond the search space, they are out of the search space. This is less than -5 and this is also less than -5. So as per the strategy that I explained earlier, in this case we will keep these values to the boundary. So this value will be equal to -5, this will also be equal to -5. So corresponding boundary, we will put these values close to the corresponding to the closest boundary, and the closest boundary is -5, -5. So your trial vector is -5, -5. Now we will apply the crossover, and in this time again the crossover, you will see that the set of indices again the both, and therefore your new x3, the offspring x3, will be the trial vector -5, -5, and here you can see that the function value is 50, while at x3 the function value was smaller. This function value was smaller than the offsprings, and therefore the greedy selection says us that the new x3 will remain as the old x3, means the offspring will not replace the parent vector. It means in this case the parent will survive because it is more fit to the offspring. So here the offspring will die out and the parent will survive. Now the same operation, same procedure will be applied to the remaining two solutions x4 and x5 with this function value and this function value, and after applying the same process, this is the updated population after the first generation. So these are the updated solutions and these are the updated function values. Here you can see that the best solution is now x2 because this is your minimum value 1.6158. This is your, so you can easily understand that in just first iteration we have modified the solution significantly from 3.07412 to 1.6158. This is the way how this differential evolution algorithm works. So best solution after x2 is this. Now we will apply the same process again for the generation 2. This is the generation 2 and here this can be observed that the solution x1, x4 and x5 are modified. So out of 5 solutions, 3 solutions are modified. In other words, I want to say that 2 parents in the next generation, the 2 parents survived and the 3 offsprings replaced the parents. Also after second generation, the best solution is this. After second generation, the same process will be applied and you will find that this is the best solution 0.02815, which is this function value, which is better than the first generation. So in every generation you can see that the uh, uh, position is updated, the function value is updated. This is all about the differential evolution.